I have a longer last name, but I just go by Palffy. And when you pronounce it, if you write it, you have to write the whole thing. And I will be teaching this course. Now there are two other people who will be involved with the course. And one of them is Professor Xiaoyu Zhang, who's a professor from the math department, and she does applied math. And the other person is Yue Sui, who's at the very back. Please stand up so you can be seen. And she will be the teaching assistant for this course. And so she's the teaching assistant for this course. Now, she's a graduate student. She's a second-year graduate student. So she took this course last year, and she got the highest grades in the class. And I'll talk a little later about her role in this class and how she will interact with you. So my email address is mpalffy@cpip.kent.edu, and my phone number is 22604. And so you can get hold of me either by email or just by calling me, okay? And feel free to contact me anytime, pretty much about anything that you want. Okay, so we need to get to know one another. I'll try to learn your names. But I think it would be useful if you could all stand up and say who you are, a little bit about your background, just so we can all kind of get to know one another. And also your name, the name by which you want to be called. Okay? And seeing as how we are videotaping everything, it would be good if you could come up, stand there, face the camera, say who you are, and a little about your background, and then we'll go through the class like that, and everybody can get to know one another a little better. So why don't we start with you, Sukhdev?
Okay. I'm Sukhdev. I started up in spring, so spring and summer, so 2 semesters. So this is my third semester, it completed. And
Where do you
background,
come from?
I come from India, and background, I did my engineering, and then I did several other things for it. And then I did my master's in physics, and out here for PhD.
Very good.
Yeah.
Thank you. So I just go one by one.
Hello, my name is Youngi Kim from Korea. My major was physics in undergraduate and graduate school in Korea. Thank you.
And what do we call you?
Youngi.
Youngki.
Yeah.
Okay, good.
My name is Shuang Zhou. I'm from China. I got my undergraduate in applied physics. That was many years ago. And I worked for the next several years. Then I came here for the PhD. Yeah. Nice to meet you.
And we call you Sean.
Yeah.
Is that right?
No.
Okay, good.
I'll leave that too. I'm Bill. I'm from here in the States, and I have my master's in physics from here, and I'm here part-time. I'm working for my PhD. I work at a liquid crystal company, Alpha Micron.
My name is Nicholas Glazer. I go by Nick. I am from California, all the way on the West Coast, and I got a bachelor's degree in physics from Cal Poly University. Here I am at the LCI.
Very good.
PhD in Turkey, and I won scholarship by my government, so I'm here for my PhD.
And we call you
Emine.
Emine. Okay, very good. Okay, go ahead.
Hello, my name is Dawei Li. You can call me Dawei, or you can call me David. I'm from Taiwan. In the last 3.5 years, I worked in e-trade. That's all.
Why do you have a signature on your on the back of
This is
your
a
jacket?
famous guitar player in Taiwan. Actually, he's my teacher. And I play fingerstyle guitar for maybe 20 years.
Really?
Really.
You can give us a concert.
I heard you play
Classical, I mean, steel string guitar or nylon? Classical?
I fingerstyle, that's not nylon. Acoustic.
Acoustic guitar.
Some marking, something like that.
Very good. Okay, we'll have to hear you at one point.
Okay.
Good. Okay. Now wait.
Yeah.
All right.
Okay, hi, I'm Cui Yuzhang. You can call me GC. I'm from China, and I got my master's degree in optics engineering and focused on liquid crystal devices. And nice to meet you.
Very good.
Hello everyone, my name is Xian Hui. My Chinese name is Xian Hui and I come from Taiwan. And in here you can call me Sean. And my major is physics in the undergraduate and graduate program. And my research in the past is little relating to the electrotunable gravity and some photoalignment issue. Yeah, nice to meet you all.
So we have two Seans. Did I hear you correctly? Yeah. So you want to be 1 and 2 or?
Maybe call me Hui.
Quit.
Yeah.
Okay. All right. Who's next?
Hi everybody, I'm Shuo Jiashi. You can call me Jia, and I just finished my undergraduate study in material physics in Nanjing University, which is in China. And hello everybody, nice to meet you.
Wait, what do we call you?
Jia. Yeah, Jia. Jia.
Cha?
Yeah.
Okay. I have to try to write down a phonetic approximation of that. Cha. Okay. Who's next?
Hi, I'm Jie Xiang from China. You can call me Jimmy. I get my master's degree in Instrument Science and Technology in Harbin Institute of Technology. Nice to meet you all.
Wait, I call you what?
Jimmy.
Jimmy.
Yeah.
Jimmy, okay.
Hi, my name is Johnny Chen. I got here, I'm from China, got here 7 years ago. I finished my undergrad in here, Kent State for physics. You guys can call me Chen.
Okay. So you're also kind of part-time, right?
Huh?
Are you part-time or full-time?
I don't know, we just...
You're not sure?
I guess.
Hi, my name is Mikhail. I got my master's degree in physics in Ukraine, in Kiev, and now I'm here. So nice to meet you.
And do we call you
Mikhail.
Mikhailo or Mikhail?
Mikhail.
Mikhail.
Yeah.
Mikhail. Okay.
Hi, my name is Jason Morvan. I'm from Ohio. I graduated with an engineering physics degree from an undergraduate, and it's nice to meet you.
Enschwitz where?
General University.
I see. Yeah. Okay, good. Okay. That's pretty much everybody, right? We have everyone. Good. Okay. So now we gotta get down to business a little bit, and so first I want to hand out the course syllabus. So please pass this around. And I like classes to be informal, so feel free to speak up. You don't have to hold up your hand and wait to be asked, so just feel free to ask questions, make comments. If you have good jokes are fine.
What do you go by? Name-wise?
Peter, you can call me by my first name.
All right.
I don't know, it turns out some students prefer to call professor so-and-so because, I don't know, they just prefer it, but I'm happy to call it Peter. Okay, so you all have a copy of the syllabus. So, okay, lecture times, nominally, we are meeting here 3 times a week from 11 to 11:50. I'll come back to that a little later. There's no textbook for the course. What I'll be doing is I'll be handing out notes, sort of printed notes kind of like this, which look a little bit like chapters from a book. And the reason for there being no book is because there's really nothing that covers all the material that I want to cover. There are many different books, but we don't want you to buy a whole bunch of separate books. There are some books that are really good to have. I would recommend those. But as far as the course is concerned, just the notes that I hand out should be sufficient. Okay, so those are my coordinates. And now I want to say a few words about the course, what the material is that we cover. And basically, it is statistical physics of liquid crystals. So of course, liquid crystals have many facets, but I want to focus on statistical physics. And so I want to talk a little bit about what the implications are, and to some extent what the main steps are that we will take to get to where we want to be at the end of the course. So, statistical physics of liquid crystals. So, basically, I want to take a really pragmatic view. I think we want to be able to not only understand what liquid crystals do, but to predict what they do. So imagine you have some liquid crystal in a cell somewhere, and you do something to it. You change the temperature, you apply an electric field, you shine light on it, you do something to it. And we want to be able to predict what happens. Okay, so not only understand it, but actually predict what will happen. Now, if you think about simple physical systems, like, suppose you take a ball bearing and you do something to it, you let go, the ball bearing will fall. And we can predict what will happen. We can predict how long it takes for the ball bearing to hit the ground. Or if you have, I don't know, a container with oil, then the ball bearing will fall more slowly, but it will get to the bottom. We can predict what happens. And to do that, typically, we just have a simple dynamical description of what happens. We say that F equals NA. And that's pretty much it, right? We just bang away, solve this problem. We have the equation of motion. We can figure out how position depends on time, and we are done. So there are some interesting aspects of this problem. So first of all, this is a dynamical description. And we need to know, of course we know what acceleration is, we need to know what forces are. And there are 2 kinds of forces that typically come into play. In this case, there's a force of gravity, which is pulling the thing down. So there's a force which is mg. But then there's also a force which is coming from viscosity, which is slowing down the ball bearing as it falls. So there's this kind of force, and there is some viscous force, and I don't want to go into the details of what the form of that is if we do that. But in general, there are two kinds of forces that come into play. One of them is a force which is coming from a potential, and then there's a dissipative force. So these are fundamentally different kinds of forces, and it's good to be aware of these. So these come from a potential, and this comes from dissipation. So as this ball bearing falls here, it causes shear to appear in the oil, molecules are tumbling around, and some of the potential energy ends up being transformed into heat through this dissipation process. So this is the story in general, and it's the story in liquid crystals also. But generally speaking, there are two kinds of forces, and one has to be aware that they're fundamentally different. And then these forces bring about some kind of dynamics. So this is the story we follow. But this is a simple situation because we just have one ball bearing. It's not very complicated. Even if you ask a simpler question, even before asking, how does this ball bearing fall, you could just ask, what are the forces acting on it when it's sitting in the bottom? What's happening here? And in this case, we would say that because it's in equilibrium, there's no motion, there's no acceleration, so the net force has to be equal to 0. So this is a simple situation, which is even simpler than dynamics, and we're just looking at the equilibrium story. Okay, so you guys are thinking, guys, we know all this is trivial. But it's nice to have this kind of an organization just to help guide us later on when we get to less familiar territory. Okay, now how does the force come from the potential? If you know the potential energy of something, how do you get the force?
Derivative.
So derivative. So derivative of the potential.
With respect to
Time.
The coordinate.
time,
Coordinate.
space.
Yes, yes.
It's a gradient of the force, right? So if we have a potential U, then the force is minus the gradient of the potential. And so if you're in equilibrium, then somehow this has to be 0, right? And if we have dynamics, we still have to be able to get the force from the potential in this way. And now what about dissipation? Where does dissipation come from?
If I have a drag force like 6
The
by
speed of the object. From the speed of the object.
From thermal
It's
motion.
complicated.
It's not just the speed, because if you were in empty space and the object was going a zillion miles an hour, there would still be no friction.
It has to do with interactions between surfaces. The surface and it has to do with interaction between particles, I guess.
It's because of thermal motion of these molecules of fluid.
What happens? How does this work?
So there's a drag force which pulls upwards, and there's a gravitational force.
Where does the drag force come from?
You can
Particles that are in the way.
viscosity 6 by 10.
It moves particles out of the way, and when it does that, it heats them up and dissipates the energy and the motion of that into heat into the medium that it's going through. There has to be a medium that it's going through, and it bumps into those particles, and that slows it down.
Right. It transfers momentum to those particles, transfers energy to those particles. Those particles in turn transfer that momentum and energy to other particles, and that's how it goes. So it has to do with temperature. The particles in here are bouncing around. And it's a complicated business of sort of repeated collisions. A kind of a simple idea that maybe we're thinking about a little bit is imagine that you have just a very simple situations. You know, you have, say, the table, and then you put a little oil on the table, and then you put a piece of plywood on the table, and then you pull the plywood. It's the same kind of story. There's some viscous force here that ends up essentially taking work from you who's pulling this plywood and heating up the oil. And if you were to kind of imagine a more ideal situation, say it's not even oil, say just air, then you have the air molecules bouncing up, and on the average, they're going either left or right. They're just going up and down. Some are going forward, some are going backward. But when they have a collision, then they end up picking up net velocity in the forward direction. So now they are carrying extra energy back down to this guy. And then when they bounce off here, they are transferring energy and momentum to the substrate. Right? So it's a kind of a repeated collision process, and the particles here are carrying both energy and momentum back and forth. Now, I wanted to mention this because both of these things are going to be important to liquid crystals, and it's good to be aware of the distinction between them. Okay, so why do we have to do anything more complicated than this, which we can already do for us? And the reason is that in liquid crystals, we have a complex system with many particles. Now you could say, oh yeah, but I mean that ball bearing also has many atoms in it. But all the atoms in a ball bearing, to all intents and purposes, behave the same way. So we can just say they all behave the same way. We can just imagine that this is some ideal single entity, and all we have to worry about is, say, the center of mass of that. Well, that is not true in the case of liquid crystals. If you have a liquid crystal cell and you apply a field, molecules in the middle will do something different than the molecules of the edges. So we sort of have to worry about the fact that it's not uniform or everybody's doing the same thing. So one idea is that there are many particles which may be doing different things. That's one reason. And the other reason is that this liquid crystal system and some other systems that we'll talk about have additional degrees of freedom. So if we were talking about a magnet, so suppose that the ball bearing was made of iron, then it could be magnetized or non-magnetized. So there's another degree of freedom inside, which would be the magnetic moment, and we would have to worry about whether the things that we are doing to it are going to change this internal degree of freedom, and how that internal degree of freedom affects the surroundings. And so in a liquid crystal, we don't have magnetization, but we have orientation of order, and that's kind of like magnetization. It's a degree of freedom. In an isotropic liquid crystal, high temperatures, you have no orientation of order. At a low temperature, you have it. Whether you have it or not determines how the material responds to external fields, light, temperature, and so on. So there are these two issues, that we have lots and lots of particles, and we have additional degrees of freedom that we have to specify. If you cool the liquid crystal down even more, it could become ferroelectric, which is kind of like being like magnetization, except it's an electric polarization. So in this way, liquid crystals are fundamentally different from simple mechanical objects. And because of this, because of these two things, we have to use an approach which is a little different from that. The simplest thing you could say is, well, let's just pretend that each molecule is a ball bearing, and that's it. We'll just write down F equals ma for every molecule. But we have 10 to the 23 molecules. So if you think about interacting particles, that's like 10 to the 23 coupled equations that you would have to solve, right? Doesn't work very well. So lots of particles, cannot describe them individually. So we have to use some other approach, and the other approach, okay, so cannot describe individually. So we have to take another approach, and the other approach is to use statistics. So talk about the average properties. So the whole business is somehow to go from that simple description where we have F equals ma for effectively individual particles. We have to somehow go, because of the large number of particles, to using some average notions, average energy of particles, average orientation of particles, average polarization, average everything. So that's why it's statistical physics, because simply we have to move to talk about these averages. Now, formally though, when everything is said and done, how do things work out? So we still have this basic picture that we have equilibrium situations and dynamical situations. This is pretty simple, because when you have equilibrium, things aren't moving, there's no dissipation. Right, so when the ball bearing sits on the bottom of this container, there's no more dissipation. So in equilibrium, only the force is zero, which means the force which is coming from the potential is zero. So in equilibrium, we have this situation that grad U is equal to zero. In dynamics, things are more complicated. We need some equation like this. Two kinds of forces going in here, and then we get some time-dependent behavior. So in statistical physics, it turns out that the free energy that you may have heard about, so we'll be talking a lot about free energy. Now, is anybody here who has not heard of free energy? Anybody who has? Just want to make sure that people are awake. Okay, so the free energy is a really fundamental notion in statistical physics, and we'll be talking a lot about it. And it turns out that this free energy kind of corresponds to mu. Okay, so that's, if you want to kind of build a kind of a rough analogy between what we'll do in statistical physics and simple mechanics, it should be that the free energy corresponds to the potential. In fact, it's called thermodynamic potential. There's different kinds of it. And our business will be, in the simple case, when we're looking for equilibrium, just to make sure that the derivative of the free energy of the thermodynamic potential is equal to zero in equilibrium. That's kind of a simple case. And when we look at dynamics, we'll have to look at the thermodynamic forces coming from the derivative of the free energy, and that's going to be driving the dynamics together with dissipation. Okay, so that's kind of the picture. Now, to actually get to the point where we can write down dynamical equations for liquid crystals, we have to go quite a long ways. And I want to start by doing some very simple stuff first. I want to talk about just simple estimation, dimensional analysis, and then we have to look at the basics of classical mechanics so that we have the framework to do the statistics properly. So that's what we're going to do. And then we start to do statistical mechanics, and then once we have the basis for that, then we start to look at liquid crystal problems, which will be of practical importance. Okay, so that's kind of the game plan overall. Okay? Everybody, any questions on this? And my sort of philosophical attitude is that because most of you, well, you all come from different backgrounds basically, and so I want to start at the very beginning just to make sure that we're all together in this journey. And you will see lots of things that are familiar to you. Okay, so my advice would be is do not look down on seemingly simple things, because often simple things have subtle and interesting and beautiful features. So don't look down on simple things. And at the same token, don't be too afraid of complicated things. You know, sometimes people think, oh, that's a really hard problem. You know, so try to approach everything in a kind of even keel. If you know it already, that's fine. You can always learn more about it by thinking about it. And the difficult things are often not nearly as difficult as they seem. Okay, so then evaluation. So there will be 2 midterms in this course, sort of a third of the way along, and then the second third of the way along. And I will give quite a few assignments, especially now that we have a TA who can help with the grading. And then we'll have a final exam. And so the grade assignment is at the bottom of the page. The midterms are 20% each. The homework is 30%, final exam is 25%. And then there's 5%, which is at my discretion. If you have been enthusiastic in the class and asking lots of questions and look interested, then I will try to give you marks, push your grade out. But if you have been late coming to class and sleeping and not telling any jokes, then it will be good. Okay, so that's kind of the game plan. Any questions so far? Okay. Now, all of you should have a calculator, which you will not need in class typically, but you will need for the homework and certainly for the midterms and the finals. So it doesn't have to be able to do much, but you definitely need one. And the other thing I want to talk a little bit about is computing. So today, computers are everywhere, and it's important that we know how to use them. There are lots of problems that you cannot do simply on paper and pencil. There are integrals that you cannot evaluate in closed form. There are nonlinear equations that you cannot solve. You know, I don't know, x equals tan x. You know, what is x? So there are lots of problems that we have to use numerics to solve, and it's important that you be able to use a computer to do simple problems like that. So simple problems are find the roots of equations, be able to integrate things. Later we'll talk about how to solve differential equations, nonlinear differential equations. It's all simple, but you need to be able to know how to do it. So certainly you need to be able to graph things. In the homework assignments, you know, have lots of problems. You have to plot this, plot something else. So you need to be able to graph things and to do simple numerics. So, and I really want to make sure that everybody is on board with these things right at the very beginning, because later on, when you'll need to really rely on these, you will be pretty short of time. So you want to make sure that you have this stuff well in place before the going gets tough. So I expect all of you have access to computers upstairs. And I expect you all to be able to use something, either MATLAB or Mathematica some language, C or Basic, Fortran, anything you want. Maple, you must be able to use something, okay? Now, is everyone here comfortable with using something to do simple calculation? Nick,
Yes.
what do you use?
Mathematics mostly.
Okay, so you're comfortable with it.
Yeah.
Mikhail,
Well, I use MATLAB and also Maple. So you said Maple.
right?
You didn't
Oh,
write it down.
Maple is fine. I don't know if we have a license for it, but
But Maple file should be free, or how's it called? Free distributed. Oh,
yeah, the Maple version, I don't know. But anyway, Maple is fine. Okay. So is everybody comfortable with that? David, something?
Maybe Mene.
Okay.
Okay.
But I urge all of you to start looking at this right away. And just make yourself plot some little graph. Y equals sine 3x. You know, make a nice graph. Label the axes. Know how to do it. Okay, know how to, where the printer is, how to print it out. And do some simple numerics. Do some simple integral. Integrate, you know, x squared dx from -1 to 1 or something. Make sure that you can do these things efficiently, because you will need to be able to do it. And like I say, the sooner you get these things in place, the better. So we'll have an assignment, you know, coming up quickly where you'll have to do something just to make sure that everybody is comfortable with it. Okay, so much for this. We'll have a website, and I'll post my notes on the website. So you'll have some electronic resources which are mentioned here. And then I want to talk a little about the role of your TA unit. And we haven't had TAs before, but I think that it's a really useful thing to have. And so what I think we should do, and we have discussed this with you, is I would like to schedule 1 hour a week in addition to the classes, which is set aside for you to meet with her to discuss course materials and get help with problems if you need help. So I think setting an hour aside now would be a good idea, and this is not compulsory, you don't have to go there, but I think it would be useful. And so what I think would be helpful is for you guys to get together with you and just talk about the course material. If anybody has any questions, things aren't clear, you can just have a discussion. And you can also say a few words about various topics at these times. And then when there are assignments, then she can give you some hints on how to do the problems. But I expect you all to do the problems yourselves, and only when you get stuck should you go to her and ask for help. So the main idea is for you to learn how to be able to do these things on your own. I encourage people to work together, but work together means everybody contributes and everybody should learn from this experience. And this worked pretty well when you guys used to study together a lot. So I'd like to tentatively set a time for these meetings, and because everyone's busy and many of you have different schedules, I thought doing this in the evening would be a good idea. Most CPIP students are here working in the evening. See, except you are not here, right?
No, that's it.
So, is that okay? Is evening okay? So it's maybe not equally convenient for everyone, but
Maybe call you at 10 o'clock at night. Call you up at 10 o'clock at night.
well, you can tell me, I'm usually here at 10 o'clock. So, any suggestions for time? When do you guys usually meet?
7, or sometimes after lunch, after dinner. So 7, 8, sometime around that.
7, I don't know. You, any suggestion?
Well, we usually start at 7 o'clock. Well, perhaps 1 hour or 2 hours.
Is 7 a good time? You guys want to try 7? I want to set a time, and then if it doesn't work, we can always shift the time.
Or we can meet later, because I just suddenly think of I have a class, robotics class, and look late.
Right.
But it depends on which day.
How many people are happy to meet at 7? Show of hands.
Happy or unhappy?
Happy, happy. Pretty much everybody. Does that include you, Yuan?
Yes.
Okay, so then let's pick a day of the week. Monday tends to be a little hectic usually, right? So Tuesday, and Tuesday, Wednesday, Thursday, Friday is not so good because it's Friday.
Yes, I have some class to teach from 7 to 9, which day I forgot, I will let you know. So you give some time, then I can find out.
Okay. All right, so let's agree that it's at 7, and then you'll tell us when you are unavailable. Yes?
When do we know how the homework turn in, and like if the homework is turning in the middle of the week, then maybe we take a couple days look at it and then we get together and talk about it.
Well, I mean, it sort of varies. The homework gets handed out when we get to the appropriate point in the class, and usually you have a week or 2 weeks to do it. So, but I think that if you need help, you can always find you even outside of this period. So the homework is not so regularly, is that accurate? The homework is not so regularly scheduled that we could choose a day based on that.
Okay.
Okay, good. All right. Now there's another scheduling issue which I want to bring up.
I have a question.
Yes.
When is the office hour?
My office hours. I will post them. I will let you know next time. Things are still somewhat in a state of flux. Okay. The other thing I wanted to talk about is classes. So nominally, these classes are for 50 minutes, right? They're from 11 to 11:50. We have 6 minutes to finish up here. And I tend to have to travel for various reasons during the year. And what I have done traditionally is instead of 50-minute lectures, we've had 75-minute lectures, which is 1 hour and 15 minutes. And the advantage of this scheme is that we start doing these 1.5 lecture events, and then we get ahead of ourselves, and then I go away somewhere, and then there are no classes, and then when I come back, then we kind of fall back a little bit and carry on like this. So this is a good scheme, and I would like to do this if everybody agrees. But that means that we would go from 11 until 12:15 rather than 11:50. Is there anybody here who cannot do this? Everybody's okay with this? Okay. None.
This works my work schedule.
It's maybe it can be accommodated. I mean, the point is it's only 25 minutes. It's not a huge impact. But it would be good if we could do this, because I think things work really better that way. Now, this classroom may not be free until 12:15. I don't yet know whether it is or not. If it's not free, then we'll just move over across the hallway to a lab, the teaching lab, and we'll just continue there. I think Chan is already planning to have classes in there. So if this room doesn't work, we'll work in the teaching lab. Okay? So we'll confirm all this on Wednesday when we meet next. Okay, so I think that's pretty much what I wanted to cover today. So are there any questions from any of you? Nothing. Any jokes? Yes?
What about, can you post the video somewhere we can access to if we wouldn't get there?
Well, I was thinking shall use it, then nobody will come to class.
What about if I promise I will?
Like, I don't know how well the video will work. I guess if things work out well, because you have to be able to hear the voice, read the writing on the board, so it's kind of experimental. But if it works, we'll make DVDs, and at least those will be available, and maybe we'll post them. I'll just have to see, what the quality is like. Okay?
Because maybe it's better if we study, like go home study, and then if I forget something, missing something, then I look back and get checked on missing.
I agree, it could be useful. I mean, that's why we're doing it, because it could be useful. But I don't want to commit right now to making these available, because the quality may not be sufficiently good, there may be other issues, I don't know. But if things work out, then certainly we'll make it available, because that's really the purpose of it. Okay. And the other thing I really want to stress again is that I'm available, so you can always come and see me, and I think I talked to Sean about this. Typically, students find this first term difficult. You have a lot of new material coming at you fast. And the important thing is that you use your time efficiently. So just sitting somewhere and not getting anywhere and suffering is not to your benefit. If you find that you're not making progress, then get help. See US, see me, talk to, the order is wrong. Talk to your classmates. Talk to second year students. Talk to higher level students. See US, see me. But don't spend time when you're not making progress. If you see that what you're doing is not getting you anywhere, change your tactic. Do something when you get things done. The only thing that matters is results. Just being unhappy and studying is not particularly beneficial. You really want to make sure that the time you spend is spent efficiently. Okay, I'm available, and I'm happy to answer questions, sort of physics-related questions anytime. Okay, so welcome once again, and I hope we'll have a good time, and we'll see you all here on Wednesday at 11.